answering all these questions. The questions are up to question 12. Okay.
So let's start. Suppose a reaction has a equilibrium constant K is equal to 1.3 by 10 to the power 8. What does the magnitude of this constant tell you about the relative concentrations of products and reactants that will be present once equilibrium is reached? Is this reaction likely to be a good source of the product? Okay, so basically, before we get to answer the question, we need to understand basically where the constant K comes from. Okay, so your equilibrium expression, basically your Kc, is basically dependent on the products of what? The reactants, basically the products of the reaction. That is, if you have a reaction, for example, involving your reactants, let's say your A and your B. Okay, so this should be a reversible reaction. So basically what you need to understand is you're going to have your products being part of that, the numerator on your K expression. Okay, over what? The multiplication of what? The reactants A and B. Then these should be raised to their stoichiometric powers. So that's why I was putting the subscripts here. So A, B, and D, and C. So basically, that's what we're trying to say. So now, what are we trying to say? Now look at this. So now, when your K is about 1.3 by 10 to the power 8, what does it mean? It means that this reaction is favoring more of what? Because if you look at your Kc, it's like the higher the Kc there, the higher the Kc, the higher the top part there. So it's like your reaction is favoring more of what? You have got higher concentration of the products. That's the interpretation there. You have a very high concentration of what? The products as compared to the reactants. So basically, explaining what this means, getting back to our question which says, what does the magnitude of this constant tell you about the concentrations? I would say that since we know that when the products and the reactants are equal, when the products and the reactants concentrations are equal, that would mean that our Kc was going to be what? Our Kc was going to be 1. But in this case, since the value of K is very big, it tells us that we have more of what? We have more of the products. Okay, so it's actually about 30 million of that times of products as compared to the reactants. Okay, so reactants are very negligible. That's why we have a very bigger value of what? Of K. I've shown from the equation. So this reaction is a very, very good source of what? Our products. Basically, it's favoring more of the products as compared to the reversible reaction. Question 2. Write the equilibrium expression K for each of the following gas phase reactions. Okay, so some of the states are not indicated, but all basically we need to understand is in this case, basically, all these are in gaseous. So we need to write our equilibrium expressions. So our equilibrium expressions basically are dependent on the products of what? The product. So in this case, we have that as our only product. I'll write it. So the parentheses indicate that you're dealing with concentration. So then on the reactants, I have nitrogen and oxygen. So these are supposed to be raised to the stoichiometric powers. So the nitrogen oxide on the right hand side has got a coefficient of a 2. Then on the left they're just single, so just a 1 and a 1. So what we've written there is our equilibrium expression for the first reaction. Then for the second reaction, what do we need to expect there? Our K is basically going to be, so we have nitrogen dioxide on the right hand side to the power 2 divided by our nitrogen gas and what? And our oxygen gas. Okay, That's what we have. Okay, so we have our oxygen gas. That's what we have in this case. Is there any question there? Of course not. So now, going back to the last one, our K expression is basically also going to be dependent on what? On the multiplication of the products. In this case, it's a different case because we actually even have two products, so it will even make more sense here. So the key thing is you need to make sure that your reactants and your products basically are raised to what? To the stoichiometric powers. That's very, very important to note. So I'll start with my reactants. So for my reactants, that one is a 1. Chlorine is a 2. Your hydrogen is a 2 and a 1 there. So this is our K or equilibrium expression for the gas phase reactions that we're given. Third question. At a given temperature, K is basically equivalent to 1.3 by 10 to the power negative 2 for the reaction that. So our reaction is between nitrogen. So we have that equation there. So we have nitrogen reacting with your hydrogen to give us what? To give us that. So now, we are now given the other reactions in relation to the same one that is above, so that we get to find the value K there. So what basically requires us to understand how the coefficients and also reversible reactions gets to differ in terms of a constant K. So now, this being our equation, which I've copied down there, let's try to come up with our K expression. So we only have a single product raised to its stoichiometric power divided by the multiplication of your reactants, where we have nitrogen and hydrogen. Of course, hydrogen is supposed to be raised to third power because that's the stoichiometric coefficient. So now, going to our A, for our first part of the question, for our A, we've been given half nitrogen plus 3H2 and what? Giving us NH3. So now, if I was to come up with a K expression for this one, what do we expect? So we're going to have NH3. On the bottom, we have nitrogen raised to the power 1 over 2. Then hydrogen raised to the power what? Hydrogen raised to the power 3. So now, what have you noticed? How basically is this equation different from the one that we had on top here? So basically for the hydrogen there is basically a 3 over 2. I'll put that, it's 3 over 2. So what is the relationship if you compare the actual equation that we had and the one that we've been given in part A? What is the difference? So basically, ultimately, I would say it's like we had to multiply by 1 over 2. Okay, it's like we had to multiply by 1 over 2 this other equation, and that is basically what got to happen there. So now, after multiplying by 1 over 2, we've basically seen that it's like we were finding the square root of this other K constant. So what am I trying to say? I'm trying to say if you try to compare these two equations that we've come up with, look at it. For the numerator here we have a 1, there we have a power 2. On the bottom there we have 1 over 2, there we have a 1. Then the other part here you have 3 over 2, there you have like just a 3. So it's like 1 over 2. So what is that supposed to mean? What is that telling us? So if we are to equate this to what we have in the actual part, it is supposed to be K itself, the values that we have, raised to the power what? Raised to the power 1 over 2. So that if you multiply the 1 over 2 with what we have, or basically, or in short, what should we multiply with what we have for us to get to have the actual value of k there? So what you're going to notice is what we're going to have for the first part, it will just involve us what? Raising our k to the power what? The power 1 over 2. And that is basically what we are trying to say. Because we've seen that. We have a 2 there, here we have a 1, 3 over 2, there we have a 3. So it's like that actual value of k must be raised to the power 1 over 2, so that it gets to give us what we have on the left. And therefore, whatever you get to multiply with any given equation, basically in this case we've seen that we multiplied the initial equation by 1 over 2, and after multiplying by 1 over 2, our value k for the question in A is going to be the actual k raised to the power what? The power 1 over 2, which we had multiplied with. Okay, so that is how you are going to find your value k. So if at all we had multiplied the entire equation by 4, we would have raised our constant there, the power what? The power 4. Now we multiply by 1 over 2, we are raising it to the power 1 over 2. So we are going to have 1.3 by 10 to the power negative 2 raised to the power what? To the power 1 over 2. So grab your calculator there, 1.3 by 10 to the power negative 2 raised to the power 1 over 2, or 0.5. Okay, so what value are you getting? So I'm getting a 1.14 times 10 to the power negative 1. That's my constant for the first part. Okay, let's go to the second part for B. For B, what has happened is we have 2NH3 giving us N2 plus what? 3H2. So this is like we've reversed our equation there. And if you come up with a K expression, it's going to involve the multiplication of nitrogen and your hydrogen, the power 3, over what? NH3, the power 2. So now if you compare this with the actual one, it's like we've just like reversed. It's like the reciprocal. What is the numerator there is basically what? Is like now the what? The denominator. So basically that's what we are saying. We deal with a reciprocal. Whenever you reverse a reaction, and that is because we've reversed it. In this case, we are talking about our reactant to be what? To be the product in the other case. So we've reversed the actual equation. So if you reverse an equation or a chemical reaction, the K basically becomes the reciprocal. So for our B, it's going to be 1 over the actual K, which is going to be just 1 over what? 1.3 by 10 to the power negative 2. Okay, that is going to be our value of K for what? For the second reaction there. So we have 1.3 by 10 to the power negative 2 divided into what? Divided into a 1. So I have 7.69 times 10 to the power 1. Okay, so which is basically just 76.9. So that is for B. Going to our C, what has happened to the equation in comparison to the original equation? What has basically happened there? So we have 2 nitrogen gas plus 6H2, 4NH3. So if you compare this equation with the actual equation, what do you think has happened there? So it's like we've multiplied that equation by what? It's like we've multiplied that equation by 2. It's like we've doubled everything. So what happens if you get to do that? So our value of K is basically going to be, it's like we have NH3 now. So the power 4, the N2, the power 2, it's like we're just like squaring everything. The power 6. So it's like we've squared the actual K. And I did mention that whenever you get to multiply any coefficient by the actual equation, basically that is going to be the value of your k as well. So it's going to be our k that we had in the first equation, the power 2. Why the power 2? Because we've actually doubled the actual equation that we had. So that's what we're going to have. So we're just going to square 1.3 by 10 to the power negative 2. Then we say what? Squared. 1.3 by 10 to the power negative 2. Then squared. So we have 1.69 times 10 to the power negative 4. So that's what we have for this question, and we are done. So in summary, what I've said is, whenever you've been given or you notice something about the equation that you've been given, the new equation. So if you notice that it has been multiplied by a stoichiometric coefficient, a certain value. So for example, if the actual value is k, if your new equation is multiplied maybe by 1 over 2, for example, if you look at the first part, if it's multiplied by 1 over 2, then your new k is going to be the actual k raised to the same power. And that is what we did even for the last one. We had noticed that that equation is kind of multiplied by what? It's doubled. So you get to raise the k the power 2. In a case where you reverse the equation, it's going to be reciprocal. That is the way to go about it. So what happens if you reverse and again you double it? It's going to be 1 over what? K squared.
Alright, so if you're enjoying this video, just wanted to let you know to say we've answered full video. There's a full video answering all these questions. The questions are up to question 12. Okay, so you can access all these solutions and the video in full using the link in the description below. So not only do you have access to this, you also have access to all the topics in chemistry. Okay, so the link has been provided for you in the description below. Okay, so this is what you can, for example, let me show you for the same very topic, chemical equilibrium. If there are concepts you don't understand, you can actually learn them from scratch. You can see I've introduced the topic, the KP-KC calculations, the ICE table, the KC-KP relationships, and all the other things that you need to know under this topic with solubility equilibrium with a detailed lesson of an hour. Okay, so you also have access to all the other tutorial sheets on other topics as well. You just right here on our site with past papers as well. Okay, so sign up using the link in the description below to have access to our full content and this video in full.
Question 4. At a particular temperature, a 2-liter flask at equilibrium contains 2.80 by 10 to the power negative 4 moles of nitrogen, 2.5 by 10 to the power negative 5 of oxygen, 2.0 by 10 to the power negative 2 of what? Of nitrogen, N2O. Calculate K at this temperature. So the given equation that we have is basically that reacting with oxygen to give us that product. Okay. So now from this equation that we've been given, we're able to come up with an expression for our K. So our products, we just have N2O raised to the power of what? 2. Our reactants, we have nitrogen to the power 2 and our oxygen to the power 1. So we are looking at the stoichiometric coefficients. Those are the ones that are becoming the powers. So now, what are they saying for the first part? So we're trying to find now the K. Okay, so we've been given the equilibrium concentrations. So basically those are just the number of moles. So we now need to come up with what? The concentrations themselves. So I'll start with the top part. We need to put the concentration of this reactant, or that product, sorry. So if you look at our product, it has been given to be 2.00 by 10 to the power negative 2 as that. So we need to put concentration because we deal with concentrations in our calculations. So we are therefore going to divide the given number of moles, 2.00 by 10 to the power negative 2, divided by what? The volume. The volume of the flask was a 2 liter, so put 2 liter. So if you divide that into that, what are we going to have? So basically we're going to have a 1 by 10 to the power negative 2. So that is going to be raised to the power 2 divided by, so we even shift now to the other part where we get to look at the nitrogen gas. So for the nitrogen gas, how many number of moles were we given? So if you look at the number of moles of a nitrogen gas, basically given to be 2.8 what? 0 times 10 to the power negative 4. So if you divide that, 2.80 by 10 to the power negative 4 over a 2 liter, our concentration is going to be what? So our concentration for our nitrogen is going to be 1.4, 0 by 10 to the power negative 4. Okay. So you do the same for the oxygen. For the oxygen, we are given 2.50. Divide that by 2, we have 1.25 times 10 to the power negative 5. So we've done our calculations there. We've substituted in the K expression. So we need to now just do our calculations correctly. Then we get to find our value of K. So after doing our calculations there, 1.40 multiplied by 10 to the power negative 4, which is part of a denominator, multiplied by 1.25 10 to the power negative 5, which is also part of a denominator. Then dividing this, we need to divide it into what? Into our numerator. So I'll do that. So remember, this is supposed to be squared. For the nitrogen, that is supposed to be squared. So after doing my calculations, the value of my K that I'm getting is basically 4.08 by 10 to the power 8. So what is my value for K in this case? So we've answered the first part of the question. The second part of the question says, if nitrogen gas concentration is what, and for the product it is what, for the oxygen it is what, does this represent a system at equilibrium? So basically our calculations are going to be based on the information given. So we try to determine the K. If it matches up with the one given from the equilibrium, then we are going to say it was at equilibrium. If it doesn't match up, then it wasn't what? The system was not at equilibrium. So let's get to do our calculations. So we have our K, of course, being dependent on the equation. So our product is N2O to the power 2 divided by our reactants. What we have? So for our reactants, we have our nitrogen gas, the power 2, and also our oxygen gas there. So we need to substitute now. For the product there, the concentration has been given to be 0.200. So squared divided by, for our nitrogen, we've been given to be 2 by 10 to the power negative 4 squared. For oxygen, 0.00245. Okay, so after doing our calculations there, what are we going to have? So I'm basically getting 4.08 by 10 to the power 8, so which basically matches up with our given our given K value at equilibrium. So the system was also at chemical equilibrium in the second part of the question. Question 5. The equilibrium constant is 0.090 at 25 degrees Celsius for the reaction that. So let's write that reaction that we've been given. So we have water, gaseous state, plus that. So by the way, A chemical equilibrium which involves all your reactants and your products being in the same phase, for example in this case all of these are in gaseous state, is referred to as homogeneous equilibrium. Okay. So now, for which of the following sets of conditions is a system at equilibrium? For those which are not in equilibrium, in which direction will the system shift? Okay, let's get to do our calculations. So
Alright, so if you're enjoying this video, just wanted to let you know to say we've answered full video. There's a full video answering all these questions. The questions are up to question 12. Okay, so you can access all these solutions and the video in full using the link in the description below. So not only do you have access to this, you also have access to all the topics in chemistry. Okay, so the link has been provided for you in the description below. Okay, so this is what you can, for example, let me show you for the same very topic, chemical equilibrium. If there are concepts you don't understand, you can actually learn them from scratch. You can see I've introduced the topic, the KP-KC calculations, the ICE table, the KC-KP relationships, and all the other things that you need to know under this topic with solubility equilibrium with a detailed lesson of an hour. Okay, so you also have access to all the other tutorial sheets on other topics as well. You just right here on our site with past papers as well. Okay, so sign up using the link in the description below to have access to our full content and this video in full.